Okay, so let me see. If you're hearing me in Pittsburgh, you can wave at me and I'll be encouraged to go ahead. Thank you. So I'm going to spend a little bit of time. Well, so here's the plan. I want to be sure that if you have questions, you have a chance to ask them. And then I'm going to talk about the midterm exam from 6 years ago. The question, problem number 4, the one about hedging a short futures position, seems to have generated the most heat and maybe some light. So let me deal with that one first. And then I would plan to go back to the problem that has to do with the Cox-Ingersoll-Ross model. And depending on how much time we have, I'll do the solution that's there, but more importantly, once I get started on that, I'll just talk about all the things that I can think of that are related to that. And so those are the 2 things that I have in mind. Let me see if you have questions before I get underway this evening. We have an hour and 15 minutes I'd like to give you a break before we start the exam at 7 o'clock. Any questions? Okay. Not hearing anything, let me talk about futures hedging. So I'll use the notation F of T. This is for the futures price of the asset S in that exercise, the price at little t for delivery at capital T. And the problem says to trade in S and the money market account to hedge a short futures position. And before we look into that, let me just do a brief review of replicating in general. So let me remind you about how we replicate a call. So we do the following. We say we want to create a portfolio whose differential is given by delta ds plus r x minus delta s dt. This portfolio at each time holds delta shares of stock, and the cash x is the amount of value in the portfolio, and x minus delta s is the amount of this value that's in cash, and so that's growing at the interest rate. And we want x of t to be equal to the call price for all t. And in order to do that, it's easy usually to look at discounted x and discounted call. The reason we look at discounted x is because our formula for dx has an x on the right-hand side. And if we look at discounted x, it removes that. And so what we do is we equate e to the minus rt x of t, the differential, and e to the minus rt call price s of t dt, the differential. Now, there are 2 ways you can think about what we're doing here. One way is you can say, well, I've got a call. I'm going to put it aside. That'll be a portfolio unto itself. And then I'm going to create another portfolio which trades in stock and money market and whose value at each time is X. And I want the value of my replicating portfolio to always equal the value of that other portfolio, which is just the call, sitting by itself. And it doesn't matter whether you say that I want the value of my portfolio to be equal to the value of that other portfolio, which is just the call all by itself. Or you could say, I'm going to put the short call position into my portfolio. And if you put the short call position into your portfolio, so if I put short call position into portfolio. Then you have dx is equal to delta ds plus r x minus delta s dt minus the short call position, and so you'll get the profit or loss associated with changes in the short call position. And so you'll get that. And now you'll want not to have x of t always to be equal to c of t, but for this x, you'll want this to always be 0, right? Because it's long the stuff we had before and short the call. And I messed that up because my cash position, let me think about this. I shouldn't have started this. What is my cash position? If my portfolio is long stock, short the call, I guess this cash position has to be call. Right, this x has a different meaning from that x, because this x is the value that's long stock, short cash typically, and short the call, and so this x has a different meaning from that x, and I wish I hadn't done this, and so I'm going to x this out, because this is going to be more confusing than illuminating, and I'd like to go to the futures situation and think about how that one works. So now the question that we were asked on this problem was to hedge a short futures position. And the discussion that I've been having on Blackboard and with people both after class in Pittsburgh yesterday and here this afternoon is, well, could we do this in the same way as we did this over here? Could I think about two portfolios? One portfolio, like this X, that holds stock and cash, and another portfolio which just holds the futures, and try to get those two portfolios to agree. So let me think about that for just a moment, but instead of calling it X, I'm going to call it Y1. This is the portfolio that holds cash and stock. Y1, I said I would call it. And the other portfolio just holds futures. But how's the other portfolio going to evolve? I mean, what is its value? What happens to it? And the answer is, if you just hold futures, if you say I just take one futures contract and I just hold it, that futures contract is going to generate a cash flow. Either futures price will go up and cash will come in, or futures price will go down and cash will go out. If cash comes in, I have to do something with it. I'm not just going to hold cash in my hot little hand. Presumably I'll invest it at the interest rate. And if cash goes out, it has to go from somewhere. So I'll have to borrow it, and I'll have to pay interest on that. And so the other portfolio, the one that just holds futures, so it only holds one contract. So it has this change in value due to the cash coming in and out. But over time, cash will accumulate, and that cash will get invested or borrowed, depending on whether Y1 is positive or negative, at the interest rate. I cannot write down a portfolio and say the value of the portfolio is just DF, right? That's no good. I've got to say, in order for it to be self-financing, holding the futures generates a cash flow, and I have to account for that cash flow. And I'm accounting for it by putting it in the money market account. And depending on whether Y1 is positive or negative, I'm either earning interest or I'm paying interest on that cash flow. Let me see how happy you are with this second equation. Or if you'd like me to write it in discrete time and then see this as the continuous time limit. What I'm going to do is subtract these two. Well, first of all, I shouldn't have called it Y1, should I? If I'm going to call it a second portfolio, let's call it Y2. let's subtract these two. So I get delta ds plus r. Here's an r multiplying y1 dt. Here's an r multiplying y2 dt, and I'm subtracting them. So I'll write y1 minus y2, and then a minus delta s dt. And then there's a minus df. And let me call x. So I have dx of t is delta ds plus r x minus delta s dt minus df of t. Okay, this is the equation that was written down first in that solution. And what this equation is saying is it's saying I'm taking the difference of these two portfolios. So what I've done is I've formed a single portfolio, and it's going to hold stock and cash, and it's going to be short 1 futures. And the change in the portfolio value is due to the change in the stock price times the number of shares I hold. The cash earning the interest rate or being borrowed at the interest rate, and there's a cash flow coming in or out, which is the futures price. And so this is where that solution started. Let me see if you're happy with this equation to start with. This is the way my portfolio that is short the futures but is investing in cash and money market will evolve. And now what do we want of this portfolio? We want it to start and end at 0. Right? So I'm going to take what I'd like, in fact, is I'd like this portfolio to always have value 0. I'd like that my position in stock and my earnings in the interest rate are exactly what's necessary to offset the changes, the cash flow that's coming in from the short futures position. And so I'd like this portfolio to always have value 0. It's equivalent to say that I want x of capital T to be 0, because we'll see in a moment that this portfolio, when discounted at the interest rate, is a martingale. And if you have a martingale which ends at 0, it can only be 0 at all earlier times too, right? You figure its value at an earlier time, you take the conditional expectation of its value at the final time, and if the value at the final time is 0, then the value at earlier times is 0 as well. So this implies because e to the minus rt x of t is a martingale, that x of t equals 0 for all t. Now, the only difference between what I've done so far and the actual problem that's on that old exam is that the interest rate, that the stock in question pays a dividend. And so I'll need to stick that in here, and then we'll go ahead and do the calculation. Okay, let me see if we're okay with anything that I've said so far. The one thing that you cannot do is you cannot say, I've got a contract, I've got a portfolio that's doing this, and I have another portfolio whose value at each time is f of t. Because first of all, f of t is not the value of any contract. And secondly, if you have a portfolio that is holding the futures, then it's going to be getting a cash flow. That money has to be accounted for, and that's what the second term is doing here. All right, so how do we adjust this to account for dividend? That would be good, thank you. So adjust to account for stock dividend. So the stock is R minus Q S dt plus sigma S dW tilde. The Q that showed up in that problem, I used an A when I was giving the lecture on stocks with with dividends because I'd forgotten that 7 years ago I used a Q, and then we discovered it when I found the old exam. So let me be consistent with the exam and call it a Q. So this is the dividend. Well, actually, QS is the dividend rate. And dx of t will be delta ds. And then in addition, there's a Q delta S dt, because I'm getting, if I hold delta shares of stock, then I'm getting dividends at rate QS per unit time per share. And then there's the other stuff, Rx minus delta S dt, and I'm going to hold the short futures position in this portfolio as well. And the first thing I want to show is that the discounted portfolio value is in fact a martingale. So let's look at dx. So where we have ds, we have r minus q s dt plus sigma s dw tilde. Then we have plus delta q s dt. And then we have plus rx dt. And then we have minus r delta s dt. And then we have minus the differential of the futures. And there's a lot of cancellation. This rs delta dt cancels this rs delta dt. So this term cancels that one. The q's cancel. Here we have a delta qs dt. Here we have a minus q delta s dt. So these guys cancel. And so we're left with delta sigma s dw tilde plus rx dt minus df. If we discount, let me do this carefully. When I differentiate with respect to the t and the exponent, I'll get a minus r e to the minus rt x of t dt. And when I differentiate, take the differential with respect to x, I get dx of t. And I don't have to worry about dx dx. Well, I don't have to worry about the product differentials because the differential of e to the minus rt doesn't have a dw. So I have only these two terms. And then if you plug in what dx is, it has an rx dt. That will cancel this. And so what we're going to get is e to the minus rt, and we'll get this term and this term only. Delta sigma s dw tilde minus e to the minus rt df of t. We have not yet worked out what the futures price is. I'll do that in just a moment. But we know that the futures price is a martingale under the risk-neutral measure. And so this is going to be something dw tilde because it's a martingale. There will be no dt term in it. So it'll be something times dw tilde. And so we see that we have a martingale, right? So this shows us that e to the minus rt x of t is a martingale under p tilde. We were told in the problem that we want to have the final value of x be 0. When we get to the end, we don't want to have any debt. We don't want to have any money. We want to have a perfect hedge. And then, as I mentioned on the previous page, but now I can make precise, if this is a martingale, then the martingale property says this. That's a martingale. And we're told in the problem we want this to be a 0 with probability 1. And so this conditional expected value will be a 0. And this tells us that x of t is equal to 0 for all t. And so we're almost done. we've got to get x of 0 to be equal to 0 for all t, so we'd want this differential to be 0 for all t. And we have a delta sitting right there. We'll figure out what this something is here, and then we will choose the delta so these two terms cancel each other, and then we're done. So we have to figure out what is the futures price. And by definition, that's the conditional expected value of S at the final time, conditioned on the information at the time, little t, when we're pricing. And then we have to remember what S looks like at the final time. Probably the easiest way to deal with this is to look at this equation and say, well, it's not going to be discounted. S discounted at the interest rate is not going to be the martingale. It's going to be S discounted at rate R minus Q. We could do that in an offhand calculation. Maybe I should do that first, and then we'll come back to this one. So when you see you have a stochastic differential equation for something, and the something that you see is showing up on the right-hand side and you don't want it there, multiplying the dt term, you can discount that away. And in the past when we've seen that, so for example here we have an Rx multiplying a dt term, we discounted at R and got rid of it. Here I see R minus QS multiplying a dt term, I'll discount it R minus Q. And so if I take the differential of e to the minus R minus Q t s of t, you'll get, when you differentiate with respect to the t and the exponent, you get minus R minus Q e to the minus R minus Q t s of t dt. And then the other term is the discounting ds of t. And if you plug in what s of t is, ds of t has this R minus QS in it. And so that R minus Q S dt here will cancel this term, and you'll only be left with that one, except it will be multiplied by this discounting that we've introduced. And so we're going to get e to the minus R minus Q t sigma s dw tilde. So this is a martingale. So compute the futures price. So what I'll do is introduce the term that makes us have a martingale. So here I'd like to see an e to the minus R minus Q capital T to go with the S of capital T. And of course, if I do that, then I have to cancel it out here, R minus Q capital T with a plus sign, since it's with a minus sign inside. Then use the martingale property and get e to the minus R minus Q little t, S of little t. And so this would be e to the R minus Q capital T minus little t, S of little t. So there we've got a futures price, and what we need here is to know what is it in the futures price that multiplies the dw tilde. So I'm just going to take the differential and find out what this something is. So I'll again start just calling this f of t. So there are two t's. There's a t right there. It has a minus sign on it. So when I differentiate with respect to this one, I'll get minus R minus Q e to the R minus Q cap t minus little t S of t dt. It's differentiating with respect to the t and the exponent. And then the ds of t shows up, plus e to the R minus Q t minus t ds of t. And this works the same way as before. in the ds of t, there's a dt term. It's r minus q s dt. And when I fill that r minus q s dt in right here, it will cancel the term that's at the beginning. And so I'm only going to be left with the dw tilde term. And so out of the ds of t, I'll get, well, there'll still be this r minus q sitting in front. And then I'll get the sigma s dw tilde. So now we jump back to here, and we said that 0 is equal to dr of t x. This is going to be a 0, but what it actually is, well, we can factor out some terms here. There's an e to the minus rt that we can factor out. And then here I have delta sigma s dw tilde, delta sigma s. I'll put the dw tilde outside too. And then here we have the e to the minus rt has been factored out. Here I put the differential of the futures price. And so that's e to the r minus q t minus t sigma s. And then we see what the delta has to be. The sigma s's are the same, and we'll get delta of t is e to the r minus q cap t minus little t. Just for point of comparison, delta of 0 then, if I plug in a 0, it's e to the r minus q capital T. And delta at the final time is, I have a 0 in the exponent, so I'll get a 1. So it says if you're going to hedge this short futures position, you start at time 0, you start with no capital, right? Because when you sell the futures contract, you get nothing for that. So you have no capital. You buy this many shares of the stock, e to the r minus q capital T. You'll have to borrow that money. And then you're going to slowly decrease your position in the stock so that by the final time you have only 1 share of stock. And the futures does whatever fluctuation it does, but your portfolio exactly offsets that. And so the value of your portfolio is always 0, and you have a hedged position. Okay, so that was problem 4 on the old midterm exam. Let me see if we have any questions about that. Okay, so you guys are happier with that than the guys in Pittsburgh. But on the other hand, most of the questions in Pittsburgh came after class, and you won't have a chance to do that. So,
Professor?
Yes, go ahead.
Actually, I got one question. If the dividend is a lump sum payment, then delta T should remain the same, right? I mean, if there's a lump sum payment at the end of the
What happens if there's what happens if there's a lump sum payment is that in the formula for the stock, at the times when there are lump sum payments, you'll see a drop in the stock price right here. And so rather than being reduced continuously at a rate, it will be reduced in jumps. The discounted portfolio value will still be a martingale. The whole business of these portfolio things is to be a martingale. And what happens with the portfolio is that if you're holding the stock and you see the stock drop, has a jump drop, at the same time you capture the dividend in your portfolio, and so the portfolio doesn't see any jump. It continues merrily along as a martingale. And so the ideas are all the same except for that modification, and you'll still get the same kind of an answer. I haven't actually worked out the calculations, but the method is clear, and I would not be surprised if I got exactly the same answer, but I'd have to do the calculations in order to know. Well, in fact, you can't get exactly the same answer, right? Because if the only payments are lumps, then there is no concept of a Q, right? So you can't get this answer. Probably what's going to happen is that whenever there's a lump payment, you'll make a jump change in your portfolio, I would guess, but I'd have to do the calculations. I've chosen to treat in class only the case of continuously paying dividends, but the text actually treats lump payments of dividends as well. Any other question? Maybe a question that I know the answer to. Let me talk about problem 2. So on the old midterm exam, problem 2 was the Cox-Ingersoll-Ross model. So it's a model for the interest rate, and it looks like this. The differential of the interest rate is a non-random function a of time minus another non-random function b of time times the interest rate dt plus sigma of t square root r of t dw tilde of t. A, B, and sigma are non-random functions of positive non-random functions of time. The point of this model, as opposed to, say, Hull and White or Vasicek, is that the interest rate cannot become negative. So you start out with a positive interest rate, and if it starts moving towards zero, the square root of r of t term right here will shut off the interest rate. And this term will be a zero as well, and a is positive, and it will push you back into positive territory. So this interest rate cannot go zero, which makes this model a lot more desirable than the others that we've seen, although it's more complex to work with. But it does have the affine yield form. So if we were to think about bond prices, so the price at little t for a bond that matures at capital T, according to the risk-neutral pricing formula, is given by that. Because the only randomness on the right-hand side of this stochastic differential equation is the differential of the driving Brownian motion, and the unknown process r of t itself will have a Markov property that says this will be a function of t and r of t. The discount process d of t is e to the minus integral 0 to t of r of u du, and the martingale here is discounted bond price. If I multiply by this, it completes the discounting inside, and so rather than starting at little t, I start at 0 and integrate up to capital T r of u du. And once the random variable that sits in here does not have a little t dependence, then I can apply the Tower property and see that I have a martingale. And this, of course, then is d of little t, f of t, and r of t. And this then was the martingale. So this question just was, use this four-step procedure and find the partial differential equation that the function f satisfies. I think that's kind of boring, and it's written down there in the notes. So let me just write the equation down, and then we'll go on and do other things with it. So what is the equation? It's minus r, f of t and r, plus f sub t of t and r, plus a of t minus b of t times r, f sub r of t and r, plus 1/2 sigma squared of t r, f sub rr of t and r is 0. This is for all times prior to expiration. We're generally not entitled to have these equations hold at expiration. In this particular case, it also holds at expiration, but that's an accident, so I'm not going to write that down here. And for all r's bigger than or equal to 0, r cannot go negative. The primary difference between this equation and the ones we've used before, well, there are two differences. One of them is I'm not assuming that a, b, and sigma are constants. So we get functions of time here in our partial differential equation. That's not going to hurt us. We're going to have to solve it numerically, but it doesn't make it any harder to solve it numerically. The other difference is this r that shows here on the second derivative. What always shows up on the second derivative is the dr term, right? Dr multiplies the second derivative, and the dr is sigma squared times r dt, so we see that there, sigma squared times r, and in the Hull and White and Vasicek, you do not get an r there because you don't have a square root of r here. And you see, by the way, that the only power that's going to work like this for us is the square root power, because if we had something other than square root, we would get something other than r there, and we want just to have terms that involve r and terms that don't involve r. We don't want to see any r squareds or r to the 3/2 or anything like that, or we're going to get into trouble. So we guess that there's a solution of the affine yield form. Oh yes, there's a final condition that this is the bond price that pays 1 at capital T, and this has to hold for r greater than or equal to 0. And we guess that there's an affine yield solution which would look like f of t and r is e to the minus r c of t, little t and capital T, minus a of little t and capital T. And then we want to figure out what are these functions c and a, and they will depend on the time to maturity. And in this particular case, well, actually in all the cases that we've looked at, we can figure out immediately what c and a are when little t is capital T, because you need to have a 1, right? This thing has to be equal to a 1 when little t is capital T, and it has to be equal to 1 for all values of r, and the only way that can happen is if the thing that's multiplying r here is a 0, because otherwise this would depend on r, and it couldn't be a 1 regardless of the value of r. So we're going to have c of capital T equal to 0. And once this is gone, then we'll have to have a of capital T equal to 0 so that we get a 1 at the final time. And then the way the affine yield calculations go is that we compute the derivatives of f. We assume that the solution looks like this. We compute the derivatives of f and we plug them into the partial differential equation. So if f looks like that, then the derivative with respect to time of f, there's a little t here and a little t here. So if I differentiate that, I'll have to differentiate with respect to those, and I'll get a minus r times c prime minus an a prime, and then I'll get the exponential back again, which is the function f. If I take the derivative with respect to the r variable, the only r is here. A minus c will come down front, and so I'll get a minus c times f. And if I take the second derivative with respect to the r variable, another minus c will come down, and so the second derivative is c squared times f. And I put all of that into the partial differential equation. And so the partial differential equation becomes r times f. F sub t is right here. So minus r c prime minus a prime times f. That's f sub t. F sub r, let's see, I get plus a minus br. F sub r is minus c times f. And then plus 1/2 sigma squared r. F sub r is c squared times f. That has to be equal to 0. And this works because the f's cancel. And then we have two kinds of terms. We have terms that are multiplied by r and terms that are not. So for example, now let me take a plus r. Here's an r multiplying a minus 1. Here's an r multiplying a minus c prime, and that's a function of little t. It depends on our terminal date, capital T. Here is a little r multiplying plus b times c. So plus b of t, c of little t and capital T. And here's an r multiplying 1/2 sigma squared c squared. And then we have all the terms that don't involve r. Here's a minus a prime of little t and capital T right here. Here's an A times minus C. And I guess that's it. This has to be equal to 0 for all t's between 0 and capital T, and for all non-negative r's. And the only way that can work is if the thing that's multiplying r is a 0. Because if the thing that multiplies r is not a 0, then the left-hand side would change when r changes. And the right-hand side doesn't. It's always a 0. And so that tells me the thing multiplying r is a 0, and so that tells me a formula for C prime. C prime is equal to all this other stuff in here. C prime of little t and capital T is equal to all this other stuff. Minus 1 plus b of t, c of little t and capital T, plus 1/2 sigma squared of little t, c squared of little t and capital T. And A prime must be equal to this, so that once this term is 0, then these two terms have to also add up to 0. And so I get A prime is minus little a of t, c of little t and capital T. If the a, b, and sigma are constant, there's actually a closed form solution for this. And there's an exercise in my book that does it. But generally, a, b, and sigma are not constant. When one uses this model in practice, it's normal to let these functions be piecewise constant and then use the values of those functions as a calibration tool to get the model to fit the yield curve data that you have. So a, b, and c are typically not constant. And so what you do is you take these terminal conditions and these equations and you just integrate back numerically from the final time, working your way back to get these functions. And so you get bond prices. And that's an important thing to be able to get quickly, because you want to, when you're calibrating a model, you have to compute the bond prices lots of times, because you compute them, you see they're not right, you tinker with the parameters, you compute them again, and it takes lots of calculations, and so it's good that you have only two ordinary differential equations to solve in order to produce the bond prices.
I have a question. How did you get this solution? What is your guess towards it?
The reason I guessed this solution was because I saw it written in a book. I don't know who was the first person to realize that there were a class of these models that could be solved by guessing a solution of this form. In my text, there's a sort of there's a description of the set of models for which this technique is going to work. That's been worked out now, but I don't know who was the first one to say, oh, look at that, this one works out. My guess is that Vasicek started this, and Vasicek sort of was lucky, and then others started thinking, well, how far can we push this? What's the set of models for the interest rate that would allow me to do this? Let me jump back to the calculation that we were doing here.
Professor, I have a question.
Yes.
How can we decide the value range of T and R in the PDE?
How do we decide the range of T and R? So little t always runs from the initial time up to the terminal time, and sometimes you can include the terminal time, sometimes not. In this particular case, the partial differential equation is also satisfied at capital T, but depending on what the boundary condition looks like, if the boundary condition is ugly, you don't always get it at capital T. So it's always that T range, from 0 up to capital T, maybe not including capital T. And for R, you have to think about what can this interest rate process, what values can it take. In the Cox-Ingersoll-Ross model, the interest rate cannot become negative for the reason we discussed here a moment ago, and that's why I take R greater than or equal to 0. In the Hall-White model and in the Vasicek model, the interest rate can become 0, and the Ho-Lee, the interest rate can become 0, and so the range here would be for all R in the real numbers.
The interest rate cannot be is in the square root, right?
So I lost part of what you said. Can you just repeat it?
I mean, in this problem, the interest rate cannot be negative because it is under the square root.
Yeah, the interest, not only because it's under the square root, So we'd have big trouble if the interest rate became negative, right? We'd get a complex valued interest rate, which would be a little weird. But in addition, the fact that this term is here, this term shuts off the diffusion when the interest rate goes to 0. And this term shuts off the negative component of the drift, and so the only thing left is a positive component in the drift. And so that keeps the interest rate from crossing 0. In the Hall-White model, this R of t was not here, and so even though this might have saved you, you still have the diffusion term, and so if you get close to 0, you can still go across 0 because of the effect of the dw tilde. I'd like to go back to the calculation of the differential of the discounted bond price. So I skipped that. Here was the formula. I said this is a martingale. We take the differential and we set the dt term to 0 and we get this partial differential equation. But if you take the differential, you get two terms. You get a dt term, which will be 0, and you get a dw tilde term. And I'd like to go back and find the dw tilde term. So when I take this differential, where will the dw tilde term come from? It'll come from the fact that one of the terms you have to do is the discount times the derivative with respect to the interest rate. Something is wrong here. That's an R of t. So there's the discount, the differential with respect to the interest rate, and then you put in the differential of the interest rate, and one of the terms that shows up in the differential of the interest rate is sigma square root R of t dw tilde of t. If I take the differential of the discounted bond price, I'll get a bunch of terms, and all of them will be dt terms and go away because we know we have a martingale, and one term only will be a dw tilde, and it will come from the time when I differentiate the function f with respect to r and then multiply that by dr, and the only term in dr that we're looking for is where does the dw tilde show up, and it's right there, sigma times the square root of the interest rate dw tilde. F sub r, where is that? It's minus c times f. So this is d of t, and then there's a minus, and then there's a c of t, f of t, r of t, sigma square root r of t, dw tilde of t.
Sorry, can you just repeat how you just calculate the previous line again? I know you just said it, but I was a little fast.
Yeah, well, it was a little fast. If I take this differential, the first term I'm going to get is I'm going to get the differential of the discount times the function f. But the differential of the discount has only dt terms in it. And I'm not looking for the dt terms because I know that there will be no dt terms because I have a martingale. So in the end, there'll be a bunch of dt terms, but they'll all add up to 0. So I'm just ignoring the dt terms. So when I take the differential with capital D, I will get a dt term, but I'm ignoring the dt terms. When I take the derivative with respect to the little t, I'll get a dt term. I'm ignoring them. When I take the differential with respect to the r, here it is, I'll get the discount, the derivative with respect to the r, and then I'll get a dr multiplying that, and dr will come from here, and it'll have a dt term that I'm ignoring, and it'll have a dw tilde term, and that's the one I'm interested in. Right there it is. And then I'll get a 1/2 f sub r, dr, but that's a dt term as well. So I've kept only the dw tilde term because I know all of the dt terms will add up to a 0. And then for f sub r, I'm plugging in what it is from here at the top of the page, and this is the bond price. So what we've got, let me put the discounted bond price up here together. Discounted bond price. And then I have a c of little t, capital T, a sigma, a square root of r of t, and a dw tilde of t. The c, again, is a non-random function of time that you have to solve for numerically. And so this is a formula for D of T, and this again is the bond price. And why am I doing this? Because now I can see what is the volatility of the bond price. I don't know whether you would rather look at the discounted version of the equation or the undiscounted version. I can see right away if this is what the discounted bond price looks like, the undiscounted bond price would have mean rate of return R plus, well actually minus bond price C sigma square root R of T dW tilde of T. We've usually taken this equation and gone to that one. Right? If you take the last equation on the page and you multiply the bond by the discount, the effect of that will be to remove this mean rate of return R and to multiply this term by the discount, and you'll come to the equation just above it. Right? I've just done that step in the other direction. The point that I'm talking about is right here I see the volatility of the bond price, and I'm going to keep track. I'm really interested in volatility vectors when we do changes of numeraire and changes of measure, which is what I'm about to do. I'm really interested in volatility vectors. We're working here with only one Brownian motion, and so our volatility vector is one-dimensional, but I'm going to keep track of the sign. So vectors have magnitude and direction. The magnitude is the absolute value when we're working in one dimension, and the sign tells me the direction, and the sign here is minus. So this together with the minus sign gives me the volatility of the bond. So it's minus C of little t cap T sigma square root R of T dW tilde of T.
I have a question with respect to this model. Like here we found the price of a bond. Suppose if we were to price, say, a caplet, we would get the same PD but with a different terminal condition. So at that time we can't use the affine yield solution to solve, right? So how do you solve that?
If we were to price a caplet, we would in fact get the same PDE. Actually, let me think about a caplet. So we would look at E tilde of D of capital T, R of capital T minus K. Let me price it at time 0. We would get the same PDE, but we would have a difficult equation to solve. And in fact, I think it's going to be easier. So there are two ways to go. One way is to first change to the forward measure. And that helps a little bit, but it doesn't help a lot. But I'm going to go ahead and do that because I'm set up for that. So what I'm going to do is say, let's think about this under the forward measure. So this quotient, D of capital T over the bond price, is the Radon-Nikodym derivative that I use to change to the forward measure. So if I divide by the bond price, I'll have to multiply by it. And B of 0 capital T is not random, so I don't need to worry about whether it's on the inside or the outside of the expected value. And then I have B of 0 in capital T, and this is E under the forward measure of the caplet payoff. And then we'd be interested in what does the evolution of R look like under the forward measure. And then we have to think about how do we change the Brownian motion. So the dW under the forward measure is the risk neutral dW tilde, and then you subtract the volatility of the bond price, and the volatility of the bond price has a negative in it. So I'll actually add C of little t cap T sigma square root R of T dW tilde dW of, whoa, what did I do? This doesn't belong here. Right? The volatility doesn't include the dW tilde. It's the thing that multiplies the dW tilde. It's the thing that multiplies the bond price dW tilde. That's the volatility. dt. And then if I go back to my equation for the interest rate, here it sits. I have A of t minus B of t, R of t, dt, plus sigma of t, square root R of t, and then where dW tilde of t sits, I'll write it as d forward, dW forward of t, minus c of little t cap t sigma square root R of t. And so let me leave the t's out to save a little bit of time. So I have A minus BR, and this gives me a dt term as well. This is a dt term, and it's somehow I've already started leaving the t's out of the sigma. It's a minus sigma squared c square root of R dt plus sigma square root of R dW forward. It hasn't helped a lot. Maybe it's helped some. This still looks like a Cox-Ingersoll-Ross model. It's just that my B has now changed. Where I had B before, I now have a B plus sigma squared C. But except for, I mean, it's the same form, but just with a different function sitting here. But at least now I'm trying to compute this, and I don't have to worry about the D of capital T term. What the effect of that is that when you write down the partial differential equation now, it will not have this term. This term, this minus RF, came from the fact that we had to do discounting. And so the partial differential equation that will describe this will look like this one, but it won't have the initial term. All right, not much progress. And I haven't answered your question yet, which is, well, how do we price this? So since you asked that question, let me talk a little bit about how we would do it. Either under the forward measure or under the original measure, it's going to turn out to be the same problem. And the problem is that if you guess an affine yield form, so you have the same, so let's define G of t and R of t to be the expected value. I'm going to go back to the original measure because that's where you asked your question. Right? If we're trying to price a caplet, we'd like to compute that. We know the PDE that G satisfies. So G satisfies same PDE. As F. The terminal condition is R minus K positive part for all R greater than or equal to 0. And we might ask, could we expect to find a solution of the affine yield form? So is there a solution G of t and R is equal to e to the minus R. I'll call it C bar now because it will be different from the C that we saw before, minus A bar of t and t. So could we find a solution like that? Well, when we were guessing that kind of thing before, the first observation we made was, where did we make the observation? That because at the final time, the function r that we were looking for had to be a 1. The function of r we were looking for had to be a 1 regardless of what positive value of r we put in here. That the c and a that showed up here at the final time capital T had to be 0 to make that work. Well, now if we look at the final time, we've got g of capital T and r is equal to r minus k positive part. And then we're asking, could that look like e to the minus r c bar of capital T minus a bar of capital T for all r greater than or equal to 0? And it doesn't take much thought to realize there's no way to make that work. Right? There's no value for c bar and a bar that you can take to get this equation to work for all values of r. And in particular, if r is below k, the left-hand side is a 0, right? If this is out of the money, you have a 0 on the left, but you always have something positive on the right. So there's no way. And then you think, well, what kind of payoffs could this work for? What kind of payoffs could it work for? Suppose we have terminal condition g of t r is equal to, say, e to the u r. U is a fixed real number. Well, then it would work fine, right? Because then we could take c bar of capital T and capital T to be minus u, and a bar of cap T to be 0, and it would work fine. So we'd be able to price things that paid this at the end. Does that help us? Well, it doesn't help us here, but it helps us if we go to the forward measure. Because if we go to the forward measure, we're trying to compute this. And if you're trying to compute this, if you knew the moment generating function of r of capital T under the forward measure, you would be in business. Because if you know the moment generating function, you essentially know the density, right? The density is the Laplace inverse of the moment generating function. And so if you know the moment generating function of r of t under the forward measure, you would be in business. But if you can price stuff like this, you can compute the moment generating function. Because, right, if you look at e forward measure of e to the u r of capital T, this is the moment generating function. And so that's the way it's done. What happens is that you can't price calls, caplets, directly, but you can switch to the forward measure. Under the forward measure, the reason I switched to the forward measure is because I want to get just the distribution of r of t. Over here, I'd have to get the distribution of a product, and that would be a harder thing to deal with. When I'm working under the forward measure, I only need to get the distribution of r of t. What I do is instead price these things. That'll give me the distribution of that'll give me the moment generating function. And then from the moment generating function, I invert the Laplace transform, get the density, and then I can do the pricing. It's a numerical method, but it's still a lot easier than solving a partial differential equation, and that's the way it's done. And one of the reasons that the affine yield models are pretty popular, I guess I should say that it's not quite the way it's done, because what one does in practice is, rather than looking at the moment generating function, you look at the characteristic function, you price e to the iu r of capital T, and then you do a Fourier inversion. There are numerical reasons why that's preferred. But this is actually part of and this is actually a substantial part of the content of the advanced derivative models class, because you do this not only in these models, but also in models with jumps. In models with jumps, you can still get this affine yield form to work, and then you can use this Fourier transform method to do the pricing. Okay, any further question about that? Let me see where I am in my discussion. What else would we like to learn tonight? Oh, here's an interesting question. Let's see. I have 10 minutes left. I mean, if there's no question about that, I'd like to do something different. So I'd like to go back to the dividend paying stock. In that case, we were looking at the interest rate is constant, and when the interest rate is constant, the forward price and the futures price are the same. Right? The difference between the two only comes about because of correlation between the discount and the underlying asset, and we don't have any correlation when the interest rate is constant, and so the forward price is given by that formula. E to the R minus Q, cap T minus little t, S of t. And you can get that from a risk-neutral pricing argument. Okay, so the risk-neutral pricing argument that derives says, well, if you enter a forward contract at delivery date capital T, it will pay you S of capital T minus the forward price that that was set at the time you entered, say at little t. And then if you discount that back to the pricing time and take its risk-neutral expected value, you're supposed to get 0. And if you write that equation down, and I'm sorry, it should be conditional expected value. If you write that equation down and manipulate it, it will imply this formula. Right? But this formula is no surprise. It's the futures price, and the futures price and the forward price agree when the interest rate's constant. So that implies this. That's not what I'm interested in today. What I'm interested in is the following. When we derive forward prices, we derive them by two methods. I did both a risk-neutral pricing argument, which is the one that I'm not doing here, but just telling you how it would go, and we also did it by a replication argument. You remember when we had a non-dividend paying stock, we said if you want to know what the forward price is, you're going to enter a forward contract at time t, little t. That obligates you to deliver the asset at time capital T. What you're going to do is borrow money and buy one share of the asset, and at time capital T, and hold it, and at time capital T you'll deliver it, and then you set the forward price so that your debt gets paid at the final time, right? That was a very simple no arbitrage argument. How does that work now when our asset is paying a dividend? That's the question that I want to ask. Okay. So let me see if the question is clear. When there's no dividend, at little t, buy the asset, you borrow S of t to do that, right, the price of the asset. And at capital T, your debt is, well, the S of t debt has grown at the interest rate, and so it's that, and so you want this to be the forward price. And that's in fact what we get if Q is a 0. But now we've got Q equal to 0, Q not 0. And what happens is, if you think about this, if you don't need to, if you do this, if you borrow S of t and buy the asset, then while you're waiting between little t and capital T, the asset's paying you a dividend. And so you didn't need to buy the whole share. What you could have done was bought less than a share and then used the dividend that was generated from that and purchased additional stock along the way, so at the final time you'd have what you need. And so the forward price ought to be less, and indeed it is. And this question is, how do you do that replication? Okay, how do you do that replication? So let me describe a method, even though we may not have the time to do the whole calculation. The method is all that you need to know anyway, right? Because you're not going to get exactly this problem, but you're going to need to know the method. So unlike futures, forward contracts have value. So if you enter, I think I'm going to do this with a forward contract at time 0. So let's enter a forward contract at time 0. So the price, right, is that. So what's the value of the contract at time t? Well, at the final time, the value is this. Right? That's what it's going to pay at the final time. You're at some time prior to the final time. So you discount back to the time of pricing, take the risk-neutral conditional expected value, and that's the value of the contract at time little t. 2 comments. At the time you enter a forward contract, it has value 0. Right? But now you start moving forward in time, and that forward contract that you entered back at time 0 at later times begins to take on value, positive or negative. And the value is given by this risk-neutral pricing formula. It's not like a futures contract. The futures contract never takes on any value because you're making these mark-to-margin payments to keep it at value 0. This thing has a value, and the discounted value is a martingale. In fact, if I discount it, so let me call this V of t, and if I discount it, this is a martingale. In fact, what I've done is I've removed the little t from inside the conditional expected value. Right? So once I've removed the little t from inside the conditional expected value, this little t, then the Tower property says that I have a martingale. If I create a hedging portfolio, a replicating portfolio, dx is equal to delta s dt plus r x minus delta s dt, then e to the minus rt x of t is a martingale. And in fact, if you compute the differential of e to the minus rt x of t, we did that a while ago. Let me see if I can remember what we get. We get a discounting, and we get a delta, and then we get the differential of the stock price, the dw part, sigma s of t, dw tilde of t. We did that at the beginning of the period, so I'm just recalling it from there. You want to know what is the delta that will allow you to replicate this forward contract? That's the question. And so what do? You work all this out. You know what S of capital T is. You know what forward price is. You just do this calculation and then take its differential and equate the differentials. So you equate this to d discounted V of t and solve for delta. You probably won't do it before the exam, but while I'm here, let me just tell you what the delta turns out to be. The delta of t turns out to be e to the minus q of cap t minus little t. So that means that delta at time 0 is e to the minus q cap t, and delta at time capital T is 1. So you buy less than 1 share and then you ramp up your position. And the way you're ramping up your position is you're using what you own, the dividends from the stock that you own, to buy more stock. And so you wind up with exactly 1 share at time 1. Okay, I'm out of time. My point here was that if you're trying to replicate some asset, take the differential of the discounted price of the asset, take the differential of the discounted replicating portfolio, and equate the two and find out how many shares of the underlying you want to hold. Let me give you your full break so you can have a chance to refresh before we start the exam.
Professor?
Yes.
One final question. So in the DX, shouldn't we add the dividend also? Because we'll be getting a dividend.
The DX does have a dividend. Yes, you're right. Thank you. So that should have a Q delta SDT. Quite right. Thank you. The discounted X, though, will still be a martingale. In fact, now that you've fixed it for me, it will be a martingale.